Hello, welcome to video 2K. This is the last video of Unit 2 for AP Calculus. And this video is about continuity, a little bit more about continuity. If you recall, we could say informally that a function is continuous if you don't have to pick up the pencil while you're drawing it. So that's kind of an intuitive notion, but we need to focus on the mathematical definition of continuity, which says kind of the same thing, but in mathematical language, and it's a little bit more precise. So this is kind of review. What does it mean that a function is continuous at a point? Well, it means three things. So remember, first, the limit has to exist at the point. Second, the function has to exist at the point. And third, the limit and the function are equal. So this limit has to exist. The limit as x approaches the point of f of x. The function has to exist, and they have to be equal to each other. Another way to think of it is that the function actually equals what is approaching at that point. Okay, so here's a good problem from the book. It says, state how continuity is destroyed. That sounds so terrible. How is continuity destroyed at x equals c for each of the following graphs? Okay, good. Well, when you look at the first graph here, we see the problem at point C is that the limit doesn't exist. As we approach from the left, it approaches this value of y. And as we approach C, as x approaches C from the right, it approaches a lower value of y. These don't match. So the limit doesn't exist. So this function, the continuity is destroyed right away. The limit doesn't even exist, so there's no point in going further. Remember, this is called a jump discontinuity, and it's non-removable. There's no fixing that. Okay, next example. The limit certainly exists from the left and from the right. As we approach C, the value of the function approaches this value of y right there. So the limit exists. Number one is true, but the second one is false. The function exists at the point. It just has a hole there. The function is not defined to be anything at C. It has no value there. So that's why continuity is destroyed for that one. All right, C. It looks like almost the same thing. We're approaching from the left and from the right. It approaches this value of y, so the limit exists. The function exists also. So part 1 and part 2 are good for this problem. But part 3 bombs because the limit and the function aren't equal to each other. The function's down here, so what the function is approaching as x approaches c is not equal to what the function actually is. So we're good for 1 and 2, but the third condition bombed. All right, this one I'll just discuss quickly. The limit doesn't exist here. From the left, it approaches this value of y. From right there, from the right, it approaches that value. The limit doesn't exist. The function exists, but that doesn't matter. The limit doesn't exist. So it's not continuous there. Okay, we did this kind of problem before, so I'm just doing this kind of as review. It says, discuss the continuity of the function below. Well, we kind of want to discuss where it's continuous. All right, now this is a rational function, and the only place where we can get in trouble is when the denominator is 0. So we know from when we're finding limits, we need to factor. Okay, so this is equal to x minus 3, and if we factor the denominator, we get x minus 3 times x plus 1. And so we kind of discussed this already when we were discussing limits. When the denominator is 0, those points are either holes in the graph or asymptotes. So if the factors cancel, that means there's a hole in the graph there. At x equals 3, there's a hole in the graph. So it's a removable discontinuity, but it's continuous there. And we see that's true in the graph here. So the limit exists, by the way. It approaches the value that where the hole is. And I think it's like 1/4. But the function is not defined there. So that's a point of discontinuity. Okay. And let me see. At x equals -1. That corresponds to the factor that didn't cancel. Well, that's where a vertical asymptote is. and that's non-removable. So the whole is removable because we could just define the function to be that value there. We could fill it in. Vertical asymptote, non-removable. It's not a matter of just redefining a point. Okay. All right, and there it is. So here's a picture of the rational function. It does have an asymptote at -1 and a whole here at 3. Sometimes you might want to know, how did I know what the y value of that is? Well, that's from the limit. So just to review, because you need to know that, this is something we did before. The limit of x minus 3 over x minus 3 times x plus 1. We're trying to figure out what it's approaching here, the y value of the whole. The x minus 3's cancel. We have the limit as x approaches 3 of 1 over x plus 1, which is 1/4. So I just kind of wanted to relate this to what we did before. Here we're just finding where it has holes and asymptotes and discussing the discontinuity. But I just want to remind you, how do we actually find where that hole is? Well, we know there's a hole at 3. How do we find the y value of it? That's what the limit is. It's what the function is approaching as we approach the hole. Okay. Now, here's a different type of problem. It says find the value of a that would make this function continuous. Okay, well, it'll be continuous if the piece on the left, which is the first piece, matches the piece on the right, which is the second piece. Okay, so the limit as x approaches 2 from the left would be this function. This is the function on the left. And, well, that would just be 2 cubed, which is 8. The limit as x approaches 2 from the right of ax squared. This piece is where we're coming. If we're approaching 2 from the right, we got to use this piece. And as x approaches 2, that'd just be a times 2 squared, which is 4a. Now, we want these limits to be equal so that the function is continuous there, so that the left piece matches the right piece at 2. So we're going to set these things equal to each other. Now, I kind of want to explain where it came from. We could have started there already. If you notice, all I did is I put 2 into x cubed, 2 into this one, and set them equal to each other. So I realized you could jump straight to this if you know what's going on. I just kind of want to explain what we're doing. From the left, it's approaching 8. From the right, it's approaching 4a. And we want them equal to each other, which means we need a to be 2. If a were 2, then these two pieces match each other. We have the graph of it here. On the left is x cubed, then it's hard to tell, but right here is kind of the border point. I just put a dot there to emphasize it, a point there. And you see the slope changes a little bit right here. This function is actually x cubed, and we found a to be 2. This function is 2x squared. And with a equals 2, they do match right there. Okay, next example. I like this one. This is a little bit more interesting here. We have some sort of oscillating going on there from a sine function. Okay, find the value of a that would make the function continuous. Okay, the border point is at 0, right? To the left is 0, this is continuous. To the right is 0, this is continuous. We just need them to match at 0. So the limit as x approaches 0 from the left of 4 sine x over x. We need to know what that is. All right, in the figure it looks like it's approaching 4, and it is. So remember this part right here, sine of x over x as x approaches 0 approaches 1. So this is 4 times 1, which is 4. And like I said, that's what we see here. From the right, the limit as x approaches 0 from the right would be of a minus 2x. Well, as x goes to 0, that's just equal to a. All right, in order for the limit from the left and the right to be equal, we need 4 to equal a. There's nothing to solve here. All right, so This bottom one would be 4 minus 2x, which is actually the line graphed here. So for this choice of A, we see that the two pieces meet on the y-axis at a value of 4. This graph is continuous. Okay. All right, now we're going to head for our last topic. This is something new called the intermediate value theorem. And it's a property of continuous functions. So let's kind of read through this. If f is a function that's continuous over the interval a, b. All right, so this is interval notation. This means all values of x between a and b, and since these are square brackets, actually including a and b. So we have a function defined on some interval between two numbers and including those numbers. On here, here's the left endpoint right here. That's the value of the function at a. And this is the right endpoint here. That's the value of the function at b. And it's continuous everywhere in between them. Now, it says that if m is a number between those two values of the function, that's why it's located here in between those two values, f of a and f of b, then the function has to cross it at some point between them. That's what it says when it's saying, then there exists a number c between a and b such that f of c equals m. Kind of what it's saying is that since the function is continuous, think about drawing this function. It has to cross every value in between f of a and f of b at least once. Right? There's no way you could draw this so that you didn't go through this horizontal line m. So every value in between f of a and f of b is assumed by the function at least once. Okay, well, let's see. This takes a little getting used to, but it's not so bad once you wrap your mind around it. We're supposed to verify that the intermediate value theorem applies to the indicated interval and find the value of c guaranteed by the theorem. All right, so here's the function. F of x equals x squared plus x minus 1. It's actually the function shown in red here. We have it defined in between x equals 0 and x equals 5, and including those. That's why there's solid dots. All right, and it's a continuous function. Now, f of 0 at the left endpoint is 0 squared plus 0 minus 1, which is negative 1. That's down here. At the other endpoint, f of 5 is 5 squared plus 5 minus 1, which is 29, which is up here. Now, what the intermediate value theorem says is that at some point, the function's equal to every number between negative 1 and 29. For instance, it has to equal 20 sometimes. If it goes from negative 1 to 29, there's got to be a place where it crosses y equals 20. And this problem's asking, well, where is it equal to 11? That's right here. So the function, because it's continuous, because we're not going to lift our pen when we're drawing it, has to cross y equals 11 at least once to get from here to there. And we're looking for the value or values. It might cross it more than once where that's true. That's what we're looking for, is the x value of c, where the value of the function is equal to 11. Now, the way we find that value that's guaranteed by the theorem is just to set f of x equal to the value we're looking for. And it has to be a value that's in between the endpoints. Okay? So, all right, now we just solve it. Actually, you could enter it in your calculator and solve it, but we'll solve it by factoring here. I'll put it in standard form. This is x plus 4 times x minus 3 equal to 0. And I get x equals negative 4 and x equals 3. Now, negative 4 is outside of the interval. That's not a value of x I'm looking for. I'm looking for an x in between 0 and 5, where the value of the function is 11. And that happens at x equals 3. And you can see it here in the graph. That's 3, x equals 3 there. So at 3, the value of the function is 11. Okay, let's try another example. So here we go. It says verify that the initial value theorem applies. That means verify that it's continuous and that this value is in between the values of the function at the endpoints. All right, and then find the value of x such that, or c such that f of c equals 4. All right, here we go. So f of 0 equals 0 cubed minus 0 squared plus 0 minus 2, which is negative 2. That's down here. Okay, f at the other endpoint, f of 3 is 3 cubed minus 3 squared plus 3 minus 2. That ends up being 19, which is right here. What this theorem is saying is that the function has to pass through every value between -1 and, -2 and 19. We want to know where it's equal to 4. Since 4 is in between -2 and 19, the function has to cross that someplace, and it crosses it right here. So we're going to find out what that point is. Okay, so we want to know for what value the function is equal to 4. Now, this is a cubic. That's really hard to do. I pulled out my TI-89 and I found that x equals 2, which tells me that f of 2 is the value we're looking for. F of 2 is 4. Like I said, it could cross it more than once. It could cross it 100 times. But the theorem says at least one time it has to cross it, because if we're not picking up our pen as we draw the function, it's got to go through this line somewhere. Okay, that's the intermediate value theorem. Now, believe it or not, it's one of those theorems that don't have a lot of practical uses, but very useful for proving some theorems in calculus. All right, we went a little long, but hopefully this was informative and the last video of the unit. This is your journal assignment. For number 1, find the points of discontinuity for the function below. Are they removable or non-removable? 2, find the value of a since the function below is continuous. I think you might get a decimal or a fraction there. That's fine. 3, verify that the intermediate value theorem applies to the indicated interval and find the value of c guaranteed by the theorem. Okay, so just a little reminder, find f of 0, find f of 3, and 0 should be in between those two values, which guarantees there's a number that makes the function 0 in this interval. Your job is to find that number. All right, good luck.